Hi, Mr. Feeney. This is Georgia Mengol, and this is the presentation for the Physics1 Project 2. This is the file that you describe what you want for this project. Okay, this to summarize a 3D environment, a complex model being moved through a complex world. The model being controlled by external forces, the model exhibiting detailed collision with the environment, hierarchical bounding areas, narrow face detection, descent frame rate, and broad face detection. Okay. And this is a more detailed description, as you already know. Let's see the thing running. If you're already seeing the graphics project, you're already familiar with this, but if not, you have not seen yet, this scene has a huge amount of polygons, around 600,000 vertices, I think, adding all together. But let's see the scene first. Okay, here's a DeLorean. As you already know, I'm a big fan of Back to the Future, and it's texturized now. In the graphics assignment it wasn't. Okay, so to select the DeLorean we press number 3 because we have 3 game objects in this scene, but only the DeLorean have the collision geometry enabled and the contact points. Okay, so if I press 3 here, now I can move it in all axes and translate it. Okay. This move is being done by translation. Is not Newtonian, because we are in the what I called control mode for the camera, where I freely control the game objects that I want, like this, just to show it working. But if I get to the Newtonian mode, if I press number 9, so the camera moves to behind the game object, and now we can control it with Newtonian forces. Like this. To the front, we can turn. We can fly. Okay, just position it. I'm learning to fly yet. And as you can see, this is a huge scene. I'm avoiding to collide just to show you. Okay. And if I start pressing W, we get some speed in the Z direction. Okay. And as you can see, I have all rotational movements like bank and pitch, and also yaw, all changing the velocities for the axis. Okay, so let's try to hit something. Let's first rotate to the sun here. Wow. Here's the speed. Okay, as you can see, let me just change to the free camera mode. And I have all the freedom in the camera too. And as you can see, we're not colliding right now. Sorry. And if I move, the collisions are being drawn, the collision geometry. Okay, this is the control camera. Right now the Newtonian and of course the collision detection is not working, just showing the collision detection is working, but it's not clamping the speeds because we're just translating the object, as you can see. Okay, it's just to show you the contact points working. So here we have contact points for the wheels. Let me try to collide it. Sorry. Here, the back wheel, you can see it is colliding with the roof of the building. And we have this back geometry too. Okay, very simple. It's like just a few polygons, and they are triggered if they are intercepting a geometry in the scene. Okay, as you can see here, how working. And if I trigger the AABB debug mode, you can see here the bounding box in red, and all the triangles that are participating in the physics calculation in green, and the normals in blue. Okay, ABB off, sorry, the debug ABB off, on and off, just to show where the object is, how it's being updated by the physics. So if I move the object up and off of the ABB, it will not trigger any ABB. If I move around to another one, it will trigger the other one. Okay, and there you can see the contact point being triggered. So let's turn this off and let's go back to the DeLorean with number 9. Okay, and as you can see, all the speeds are clamped to 0 if we hit something, like here. We hit the front part of the DeLorean, and we can get out of the collision easily. And I just want to demonstrate that we can also, like, just the rotation is also being stopped, as you suggested in your file, in the description of the project, like this. Let's just start rotating and get out of the camera mode. Wait for it. Wait for it. I put too little rotation, but still. Oops. Yeah, over there. So it clamped the rotational speed. Back to it. We can get out of the collision. And just to test it, let's bank this way. See? It stopped. Okay then, so let's review your file to see if we are accomplishing all the requirements. Environment is a complex 3D model of at least 100,000 triangles. As I said, I think we have around 600,000 vertices. That will do, I think. And as you can see here, let's just stay here. Let's use the free camera mode. So we have a lot of geometry that we can collide, and all of these are being used by the AABB system. Okay, so to test, we can pick any point of this city and check that there is an AABB there, and that you can collide with something. For instance, let's select the layer again. Let's make it fly. And let's get a faraway point. Random. Come on, it's 2018 already. We need flying cars, right? 2015 futures is now in the past. So random, collide with something here. See? Okay. And collision causes entity to stop, as you saw, in the direction of the collision. In other words, if the ship is flying down and forward, well, I think the ship will continue to move forward. Okay. I did understand that, I think. Let's get back to it again. So a hierarchical AABB or equivalent is implemented in at least one of the models and can do this for both. Okay, so let me explain here the AABB. And I already put this in the README file, but probably it's clear to explain here. The AABB is being calculated during the load of the mesh if we want to calculate for that mesh. In this case, the AABB is being calculated for all the geometry except for the helicopters and the clouds, and also the trees, because the trees have all have a alpha channel, so you may not see what you're hitting, right? But as you already saw, I have a lot of collision points to test. And what the system does is to produce an ABB for every vertex, and it check every vertex and produces an ABB for that vertex and calculate the ABB unique ID. And if the other vertex is inside that ABB, it will not create another ABB, of course. And so all the triangles are inside at least one ABB. But if they span for another ABB, as I can show you, let's see. If here we can show this. Yeah. For this ABB, we have a triangle right here in the bottom of the screen that is there is spanning from inside the ABB. This is because one of the vertices is inside of the ABB. Okay, so it's been calculated like that. But if you don't have a geometry, for instance, here's the place that would have an ABB if we had a geometry over there. Okay, so there's no ABB being generated for that place. And what the system does is it checks the position. Let me get back a little bit. The first thing is calculate the extents of the game object and produces an ABB for that, just like the other geometry. And the code for that, it's right here. Let me show you in the so-called ABB manager, I think. No, in the physics here. So we take the mesh max extent and put in the diameter and calculate a sort of ABB for that encompass all the geometry of the mesh, and we have a big box with the mesh inside of it, and we calculate all the vertices for that box. After that, for each vertex, we calculate an ABB, just like for the generation of the ABB. And if there's already an ABB there, we calculate the ID of that vertex. And if we already have an ABB for that ID, we check for that geometry for collision with all the vertices. Sorry, with all the triangles in that ABB. I think you got the idea, right? Like this. Okay, when the gaming object is inside an ABB, it is checking for each of those green triangles if it's colliding with that contact points. Okay, I think we have that. So collision details are shown on the screen at an appropriate detail. You already saw that. Entities controlled by the user in 3 translational degrees of freedom. You can control this in the control camera mode. And bonus, entity has 3 rotational degrees of freedom, controlled by the user. We have that, as I can show you. This is rotational around the y-axis, and rotation around the x-axis. Let's get back here. And rotation around the z-axis. Okay. Motion is controlled by forces and not direct updates. So when we are in the follow camera mode, the motion is controlled by forces. So here I'm increasing the z speed, and here I'm increasing the rotation around the z-axis, and here I'm decreasing the rotation, and I can slow it down. Okay, now it's free. So you talk here about acceleration, but changing the velocity, it's literally the same thing, right? So movement is simulated in discrete real-time step. This is made by the delta time in the physics part of the program. So it's independent from the frame rate, because it's calculated by Newtonian laws, right? The text is reasonable small, approximately 10% size of the ship, collision detection point. It's clear that a portion of the character has collided with word. As you saw, where is the DeLorean? So if we hit number 3 and number 9, get back to it. Okay. So as you saw, the collisions are being drawn. Just show it again. Okay. And the exact point of the collision here, because 2 of them are hitting the geometry. Okay, they are being shown, and the other parts, like the back part, is not being drawn. The left wheels also not being drawn. Okay, some additional item to assist locating the character's location in the world. Lighting, shadows, pointing environment. So I think it's pretty obvious where we can locate the DeLorean, because when the scene starts, it's right in front of the camera. But we have other objects here. For instance, if I press 1 and number 9, I just selected an helicopter. If I press 0, I can release it, and it keeps moving because I started a velocity along the z-axis. Okay, those helicopters don't have any collision geometry, just the DeLorean for this project. And if you want to get back to DeLorean, hit number 3 and 9. You're back. We're back from the future. I'm just tired. Okay. Okay. I think that this part that you see here. Where is it? Okay, here, collision causes entity to stop. It does, in the direction of the collision. I don't think I implemented that. In other words, the ship is flying down y-axis and forward z-axis while hitting the ground. The ship will continue to move forward. Now, when it encounters a collision geometry, it just stops. It's almost 8:30 p.m. I don't think I will have time to implement this because I still have to upload the video and submit, and still have to do another project. But okay, I think for the rest of the things we got pretty much all the requirements. So, Mr. Finney, thank you so much for your patience and your attention, and I hope you liked the project. Bye bye.